Thanks for the introduction. I'm Zhang from the Max Planck Institute for Informatics. My supervisor is Andreas, and this also is a joint work with Yusuke Sugano from the Osaka University. So our work is about eye contact detection. It includes two cases. The first case is object eye contact, which means that the user looking at the object. And the second case is that human eye contact, which means there is a second person looking at the user. So if we can do this eye contact detection, we are able to apply this visual attention cue for the different application to estimate if the people looking at the object or looking at the user, he or herself. So the application including some interaction with the public display, attentive user interface, egocentric setting, or robotic interaction. The most related work to ours is this work from the UIST 2013, where they first detect the face and then detect the eyes. They crop the eye out to train one eye contact detector for the camera. So they are judging whether there is a person looking at the camera or not. And so because they treat the camera as the target object instead of the object around the camera, so it's the main limitation for this work. And of course, you can also train one specific eye contact detector for one specific object with this method, but in that case, you need human annotated data to train the model. And another intuitive solution will be directly use gaze estimation to estimate whether the person looking at the target. Here I introduce two state-of-the-art appearance-based gaze estimation which can be used with ordinary web camera. And the first one is our work from the CVPR 2015, and in which we apply the convolutional neural network for the appearance-based gaze estimation. Most basically, we train the model on the laboratory setting data, and then we test it on the real-world data, so that this model really can be used for real-world application. But the accuracy is about 14 degrees. And in CVPR this year, another group improved the accuracy to be 7.8 degrees. But as you can see, the estimation error is pretty large for this appearance-based gaze estimation. And also, you need the camera and camera object calibration to project the gaze direction in the camera coordinate to the object. And in general, for those group or method, you also need the personal calibration to really improve the accuracy, which we also want to avoid. So, the goal for this work is that we want to propose an eye contact detection method that it can work with ordinary web camera, and we want to apply the unsupervised learning so that there are no human annotated data. And at last, we don't want any calibration, including personal calibration, camera calibration, or camera object calibration. So the basic idea is that we assume that the target is the salient object nearest to the camera, so that we propose a method that you just need one camera and put closely to the target object. So for the real-world everyday setting, there will be plenty different objects in front of the user. And what we need to do is just put one camera to the target object, closely to the target object, and we collect the data through the camera during the daily interaction between the user and the different objects. And then we label those samples to be positive and negative with unsupervised clustering. So most basically, how our method works. With the camera attached to the target object, we collect a bunch of images from the camera, and then we perform the face and facial landmark detection. Now with the face as the input, we perform the appearance-based gaze estimation with one of our peers' work. And for this appearance-based gaze estimation architecture, we output the gaze direction in the camera coordinate. And then we project this gaze direction in the camera coordinate to the camera plane with the dummy camera parameters, which is fake parameters, so that we don't need the camera calibration at all. In this case, the project gaze point on the camera plane is not accurate, but it doesn't matter for our method. We just need to know the relative position. So for each sample, you will get one gaze location on the camera plane. And if you have lots of multiple input, you will get a distribution of the gaze location. Let's take a look over this gaze location. And you can already see that in this gaze location distribution, there are different clusters belong to the different objects. And here is the result from the density-based clustering. And remember, for this camera plane, its origin is the camera position. And the assumption for our work is that the target is the salient object nearest to the camera, so that we just need to pick up the cluster nearest to the camera to be positive cluster. And all the sample belong to this positive cluster will be positive. And the sample belong to other cluster will be negative. And also we introduced a so-called safe margin as indicated here as the green circle here. It's calculated by the standard deviation over the positive samples, that all the sample outside of the circle will be directly labeled as negative, so that we have more distributed negative samples. So far we get the labels for the samples as positive and negative. And besides the gaze location, we also extract another feature from the appearance-based gaze estimation architecture, which from the first follicular layer, and we call it phase feature, which is 4096 dimension. And we train the eye contact detector with this phase feature. So in summary, we use gaze location to do the unsupervised clustering to label the samples, and we use the phase feature to train the detector. During the test, you just need to pass through the input image to the gaze estimation architecture to extract the phase feature and feed it into the eye contact detector to predict if it's eye contact on or off. Okay. So to evaluate our method, we collect one data set under a real-world setting. It includes two parts. The first part is object-mounted data, which is recorded with everyday working environment. So we have the target object in front of the user and also corresponding cameras. And it was recording during the normal working day, and we collect a sample from the interaction between user and the different objects. In total, we have 14 participants, and each of them recorded 3 objects, which is tablet, working display, and a clock. And especially for the working display, we have 3 camera positions, which is above, below, and next to. So the second and third row are the example of the data set, and also detected face. And the second part of our data set is called head-mounted data. So this is recorded with everyday social interaction. And in this case, we let the participant wear a head-mounted camera, and we ask them to go to street to interview people. So they will really talk to different people. And in total, we have 3 participants, and we record 28 social interaction. On the right is the sample from our data set and also detected faces. So during the experiment, we used the MCC score for the error metric, and 1.0 means perfect prediction, 0 is just a random guess, and -1 is completely wrong prediction. And for each evaluation, we use the first 75% as training and the rest of 25% as test. We also manually annotate 5,000 samples from the test set to report the value. And there are no label for the training part. And for the object-mounted data, we treat each recording session individually and average the results. And for the head-mounted data, we treat it as one recording session. Okay. So we take the gate locking as one of our baseline method, which is one of previous work. And also we evaluate the usage of the gate location P and the phase feature F. So for our method, we use the gate location for the clustering and the phase feature for the detector training. And for the second method called phase clustering, we use the phase feature for both clustering and detector training. And for the second baseline called the gate classification, we use the gate location for both clustering and detector training. And the next baseline is called gate projection, which is directly use the gate location P as the visual attention, so that it judges whether this gate location P is inside the target object or not. And the last baseline is called head orientation projection. It's use the head orientation as a visual cue to judge whether this head orientation is pointing to the target object or not. So here is the main result from our paper. We test all the methods for the head-mounted data and also for the object-mounted data and also head-mounted data. So you can see our method from far left performed best over other baselines. And most specifically, for the phase clustering, it uses the phase feature for clustering and detect training. We think it's not good to use this phase feature to do the clustering because the face appearance can be different, even if the person is looking at the same target due to the different head poses. And for the gate classification, which use gate location for clustering and also detector training, we think it's not good to use this gate location to train the detector because essentially this gate location is just two-dimension feature. It's not able to capture the larger variation on the face appearance. And for the gate projection and head orientation projection, they are suffering from the raw estimation error, which is gate estimation measurement and also head orientation measurement. And also they suffer the error from the camera and camera object calibration, which we did manually for those two methods. And at last, the gate locking also performed very badly in our experiment. It's not because that this method is not good. It's just due to the fact that they have different definite concept over the eye contact. So here is the example from training set of the gate locking. The first row are the positive sample, and the second row are the negative samples. The first row actually is the person looking at the camera, and the second row is just 5 degrees off the looking camera direction. But the second row actually could be positive in real world case, especially also in our evaluation data set. And the fourth row, that directly looking camera actually should be negative because the camera is not our target object. Okay. So next, I want to show you the result of our unsupervised clustering. The first row are the recording setting. The blue rectangle is the different attractive object. The green rectangle is the target object, and the red one is the camera position. The second row are the clustering results, where the green dot are the positive and the blue dot are negative. So for those samples, I don't have the ground truth for them, but we compare those with the the ground truth in a test set, and we found that they are quite correct. They picked the correct cluster. And you can even see from this clustering that they corresponding to different object, attractive object. So the last experiment I want to show you is the performance across different objects and also the camera position. So for the left figure is the performance across the for the tablet, display, and the clock. And our method performed best for the tablet because it's kind of attractive to the participant, and also it has a reasonable size. We play the image and the video we download from the internet and attract the participant's attention. And the performance on the display is worse than tablet because it has much larger size. And the performance for the clock performed the worst because people usually don't look at it. And the right figure shows the performance across different camera position around the display, which is above, below, and next to. And you can see that our method performs robustly for those different camera positions. So we have lab demo this evening, and you are welcome to test our system by yourself. Now please enjoy our result samples, and thanks for your attention. Any questions?
Before we go into questions, I have the honor of giving you the honorable mention for this paper.
Thank you.
So there are three, because there are three authors. So congratulations.
Thank you.
And so we have time for questions.
Just a quick one. You have various clusters that arise when you set up your objects.
Yeah.
And correct me if I'm wrong, the reason why you're putting a camera under each of the objects that you want to look at is because you have no other means of labeling those clusters. Is that right?
Yes, exactly. Yes.
Okay.
Yeah.
Further question? I have one. So you chose to use an unsupervised method, and so the question is, for creating a data set, would it have been useful to use sort of a full-featured eye tracker to create a large real-world data set in order to have sort of supervised methods afterwards? Or do you think sort of the unsupervised method is as good as it gets?
So yeah, of course you can use some commercial eye tracker to do this eye contact detection, or you just use it for the training, right? Is what you mean, right? Yeah. But in real world setting, that it's not. Sometimes the camera position is different. If you train one model for the specific object and camera position, you cannot apply for other settings. But for our method, you just need to put the camera to anywhere around the target, and we just collect the sample, and after a few hours, you can get the eye contact detector for that case.
Do we have further questions? And I think with this, we thank you and all the speakers of